Okay, let's start the heat transfer in a tube. This is the not only chapter 5. Chapter 5 is just a little bit introduction. It extended to chapter 6 about this topic. This topic is extremely important in heat transfer. You know, all the heat exchanger, heat transfer design, basically the heat exchanger design, eventually the application for heat transfer. So usually your heat exchanger, you see always tubes, right? Pipe and tubes inside the heat exchanger. So we really need to know the heat transfer, convection heat transfer in the tube. I think we did finish the boundary layer, right? Flat surface. With the video I post on Wednesday. Wednesday is for the turbulent pipe flow. I'm sorry, turbulent boundary layer. You have some equation to calculate the shear, to calculate the heat transfer on turbulent boundary layer. Laminar, we covered it before, right? So again, there's many equations, okay, in this topic. And you have to, you know, I would suggest if a best way to learn, for example, if you have a final exam to go, for example, you're allowed to bring a equation sheet. This is the perfect example for this type of final exam. You know, you bring an equation sheet, okay? So you can solve problem if you can pick the correct equation on the equation sheet, right? So the link is, for solving a practical problem and your equation sheet is you have to fully understand the physical problem. Okay, so is this flow, for example, for the boundary layer, is this flow laminar or turbulent? Okay, so if you decide, okay, it's turbulent, then I go to my equation sheet. Okay, I will write a very nice equation sheet, laminar and turbulence. Okay, so turbulent boundary layer. Okay, I have a bunch of equations. I must choose the equation from this category, right? So see, that's the example. Then you goes to, okay, does the problem ask me to calculate the frictional force resistance or ask me to calculate the heat transfer? Okay, so on your equation sheet, under turbulent boundary layer, you have 5-6 equations. Some of them are related to the shear, skin friction coefficient, shear stress, shear force, right? Some of them are related to heat transfer. Okay, Reynolds analogy. Okay, remember, in turbulence boundary layer, you don't have an analytical solution like laminar boundary layer. So you have to go through the Reynolds analogy, right? Stanton number, Nusselt number, and the CF. So if you have a CF, then you can actually calculate the heat transfer coefficient based on the Reynolds analogy. Okay, so then it's Prandtl number, Stanton number equals to the CF, right? So you get a Stanton number calculated based on the CF. In Stanton number, you have H. So that's the approach for the turbulent boundary layer heat transfer calculation. With the heat transfer coefficient, you should be able to calculate the heat transfer rate. Okay, so that's approach. Same thing later. Today, we're going to talk about in the tube flow. In laminar, you have a bunch of equations from analytical solutions. Basically, in laminar flow, boundary layer or tube, you will have analytical solutions for friction, for the Nusselt number, heat transfer coefficient, those things. But in turbulence, in turbulent flow, then you don't have an analytical solution. You only have an empirical experiment solution for CF. Okay, then based on CF, you use Reynolds analogy to find your heat transfer coefficient. Okay, so that's the approach, remember. Now we are going to look at the tube flow. Okay, it is, let me tell you the section on tube flow. Okay, laminar tube flow. We'll start from chapter 510. Let me share my screen. Oh, I need to open the whiteboard first. Let me start a new page. Just give a second, my computer is slow. Next semester, I will ask the department to change the computer for me. It crashed a couple of times during the Zoom. It's not in this class, but okay. New documents. Okay. Now let me share it. Okay. Can you see the empty screen? Give me some response, huh? Any of you?
Yes, sir. We can see the screen.
Great, thank you. Okay. So this topic is heat transfer for tube flow or pipe flow. In the book, it says tube, okay, but actually, most of the application you can also call it pipe, right? So laminar and turbulence, again, laminar pipe flow, okay? So two topics, right? We want to look at the flow, which is resistance, shear, okay? And then we will look at the heat transfer, which is Nusselt number, heat transfer coefficient, right? These are the things, okay? But laminar and turbulence are different. Let's do this. In the flow phase, when you look at flow and the heat transfer, flow, which our goal is to find the resistance force, shear force, okay? This is our goal. So for laminar and for turbulent pipe flow, the shear force, the way you find out the shear force is the same, okay? So I like to talk it here all together. So, okay, this is a different approach. Okay, let's see. And in pipe flow, usually we have a head loss. I'm out of letter. Okay, let's say loss. Frictional head loss. Okay, so what does the frictional head loss means? This is delta P over gamma. You know what gamma is? Gamma is, okay, rho G. Okay, I think most of you did my fluids class, right? Or you are taking fluids class. Now you know what gamma is. Okay. So head loss equals to delta P over gamma. Okay. So, and head loss basically equals loss. There is something called Darcy-Weisbach equation. Okay, this is the equation. So based on this equation, you should be able to calculate the delta P, pressure, right? Then the pressure, let me tell you the big picture before I move on to detail of this equation. Okay, now if you have the head loss times gamma or delta P, so delta P times the cross-sectional area. This is the force, resistance force. Okay, is that right? This is a different approach, okay. But what I want to show you next is actually we can still go through the shear, right? So shear stress will be Ft divided by surface area, the entire inside of the tube. Okay, is that right? Okay. So in that sense, you should get another equation based on this. So you can substitute. Delta P is this. Delta P is something this. H this thing times gamma. So you can substitute that into this equation. You will get equation 5.113 in the textbook. Okay. Shear stress 1 over F equals to rho V square. Okay, you notice sometimes I use U, sometimes I use V, okay? When I use V, that's more general discussion, okay? If you have a flow, 1D flow, but it's general, we talk about generally, not particular problem, I use V, okay, as the velocity, okay? Sometimes if we are talking about a detailed problem, we decide it's 1D problem, and if you solve a problem, I use U, okay? Particular problem, you know, okay, I'm talking about the X directional velocity, Okay,
So
so
Dr. Zhang,
yes,
is that under the F for that last one? Is that an 8 or is that gamma?
8.
Okay.
Okay, you substitute this two relationship together. Okay, they are same equation. Basically, it's just derived from this. Okay, so cross-sectional area is quarter pi d squared, right? And the surface area is what? Surface area is 2 pi d times the length. Okay, the L and L can cancel, you see in the equation, then turn out to be this equation. So this is the same approach, okay, same thing. So if you want to go through shear stress times the surface area, you will get your F shear, total shear force, total resistance force, right? Frictional force, okay? That's a goal. In whatever you talk about, in the boundary layer, flat plate, or in the tube, for the mechanical part, you just want to know the resistance, okay? The friction force, right? Does that make sense? I'm talking about that from engineer point of view, okay? Because why you need the resistance or shear or frictional force? Because that's a force you need to overcome to make the flow like this. So what do you mean by make it happen? You have to put a pump there to pump the flow. You have to give it a power to make the flow to overcome the frictional force. Is that right? I just trying to give you a big picture. Why we need to know this. Eventually, this F shear times the flow velocity. F times V is the power. It's a power input. Okay, you have to input that much power to make the flow with certain velocity, let the flow become reality. Okay, so that's the pump power needed for the system. Ideal pump power needed. Actually, you need more, right? Pump has some, efficiency, so you need more. But ideally, you just need to overcome the frictional force. Okay, the power supply into the pipe. So that's why it's important to calculate the shear force, the resistance force, or the frictional force. Then it times multiplied by the velocity. That's the power input, the power required, needed to make the flow happen. Okay. So I want to emphasize the importance of the thing we learn. Otherwise, why we learn, right? Okay. So you can have two approaches. You can use this equation. Okay, you directly calculate the shear. Don't worry about the F. I will talk about the F in a minute. Okay, you can use this equation, then multiply by the total entire surface area of the tube to calculate the shear force. Okay, or you can use this equation. Okay, then calculate the delta P, the pressure drop. Then delta P times the cross-sectional area. Notice the two areas are different. Delta P times the cross-section area is also equals to the shear force. Okay? Is that okay? Everybody understand? You have two approaches, serve the same goal. Okay, I want you to fully understand. Either one, doesn't matter. Because these two equations doesn't matter. Everything is, the value, it's given, right? Velocity, length, diameter, 2g. Here is rho v square, okay? The only thing, they share same F, okay? So the only thing is you need to find out the F. F is called friction coefficient. Okay, it's called friction coefficient. Okay, so it's an empirical value. It's a coefficient. So there's no theoretical derivation for the F, at least for the turbulent flow. For laminar, probably you have an analytical solution for the F, but most of the time you're dealing with the turbulent flow, so you don't have a theoretical analytical solution for that. So we're going to use something called Moody diagram. It's a chart. Okay. It's a Moody diagram. We're going to talk about this in fluids class too, okay? But we need to use a Moody diagram to find the F, okay? If you know the F, then you can calculate your head loss, or you can calculate your shear, then multiply by area, or multiply by area here, delta P. Then you can find out your shear force, okay? Frictional force. Then you can calculate the power needed to drive the flow, okay? So Moody diagram, where is it? It's in the textbook. Actually, it's in chapter 6. Okay, chapter 6. I think it's on page 283, figure 6.4. Don't worry, I'm sending you that figure, okay? To group me. Give me a second. I'm gonna talk a little bit about that figure. It's important. Okay, I sent it. Did you see it?
We see it.
Yeah. Okay. So how to use this thing to find the find your, so the y-axis, the left side of the y-axis, the left side of the y-axis, it is f value. Okay, so it's the y-axis. Okay, I have one more student joining. Okay.
I'm sorry, Dr. Zhang, what page is this on in the book again, or do we have access to this Moody diagram?
283, that's a page. Okay, figure 6.4. Okay, but you can look at, I think you can look at the figure I sent it to you. Okay, same thing. So important, the Moody diagram, if you're working in industry, everybody need to know that, right? So y-axis, in the left of the y-axis, this is the f value, okay? So the bottom axis is Reynolds number. So in order to get the f, you probably need a Reynolds number. You need Reynolds number. So do you know how to calculate the Reynolds number for the pipe flow? It's different than the flat plate. It's velocity times diameter divided by kinematic viscosity, or you use dynamic viscosity, then you rho v d divided by dynamic viscosity. Okay, notice in the quiz problem we did, actually there are two properties given, right? In the first problem statement, they actually give you a mu, the dynamic viscosity. Then in the plot I give you the second, for the properties, it gives you the kinematic viscosity. Okay, they are exactly the same actually. But if you use the first one, you're gonna use this equation for the Reynolds number. If you use the one I give you, you're gonna use this equation. Okay, that's the difference. It's dynamic viscosity and the kinematic viscosity. They have different unit, and the equation look different with the difference of the rho in the numerator. Okay, be careful. So this is the Reynolds number for the pipe flow. So D, diameter. Okay, so that's totally different idea of the Reynolds number here. Okay, diameter don't change in a tube, in a pipe. Okay, so in each type of pipe flow, in each tube flow, you have only one Reynolds number. Okay, in the flat plate boundary layer, your Reynolds number changes along the x direction, right? Every location will have a Reynolds number. You have an overall Reynolds number. Okay, but here in pipe flow it's easier. Okay, it's just one Reynolds number. Okay, so that's what it is. So you calculate the Reynolds number. That's the bottom axis of the Moody diagram. Okay, so you see there's many blue curves inside this plot. Okay, each curve represent a different surface roughness of the tube or pipe. Inside surface roughness. That makes sense, right, guys? Because we are talking about the friction, right? Is that right? Friction, of course, is dictated by the surface roughness. Okay, the surface roughness here, you're talking about a relative roughness. It's the surface roughness divided by the diameter. Okay, it's K over D. Okay, they use, I'm sorry, they use E, epsilon here. So epsilon is the average height of the surface. Okay, surface is, if you use microscope, you look at it, it's not flat, right? It's not smooth, or just like mountains. Okay, so the average height of those mountains, that's epsilon. Okay, divided by D, that's called relative roughness in reference to the diameter. Okay, so it depends on different material. Let me send you one more plot here. In this plot, okay, I'm sending you. This is not on this textbook. Okay, I'm sending you a plot you can use for your different calculation. It gives you the surface roughness. It says K here, but it's the same as epsilon in your Moody diagram here. So this is the surface roughness in millimeter or in inch for different type of surface, different materials. Okay, so it starts from smooth surface, which is glass, plastic. Okay, PVC pipe, maybe you can consider it as a smooth surface. Okay, copper, brass. Okay, then wrought iron, steel, then asphalted cast iron. Okay, different type of material here. Okay, they have a surface roughness. Okay, so based on this surface roughness, you go back to the Moody diagram. You can pick a line, pick a curve, blue curve. Okay, for example, if my relative roughness is 0.002, okay, I find the 0.002, there's actually a blue curve here. That's my curve. So based on my Reynolds number in the bottom, okay, then you can find a point on that blue curve of 0.02. Then that value to the left axis is your F value, friction coefficient. Okay, anybody? Everybody can use this? It's not difficult, right? So based on the table, based on the material of that tube, you will have a surface roughness, okay? Then based on the flow condition, you can calculate a Reynolds number, which is the bottom axis. Roughness is right axis, okay? Right axis. Then pick a curve that belongs to your surface roughness and use your Reynolds number to find your F value. Okay? Is that clear enough, everybody here? I have 6 of you here. 7?
Yes, sir.
Okay, 100% clear, right? It's not difficult. Okay. So that's it, right? Then you find your F, you find your shear, you find everything else. Okay. Then you find your total frictional force, frictional loss. Okay, so that's the first topic here, the flow part. Okay, very important. I really want to have a class like this and teach you the important things. It's really good for your work. Okay, in the future work, the knowledge is important here. Okay, next. Oh, how do I turn to the next? I need a new page. Now, for the heat transfer part, flow part, heat transfer part. Flow part, that's it, okay? Oh, flow part, actually, there's the analytical solution for the laminar. Let's see, I think there's analytical solution for the velocity, I think somewhere. Let me see. So yeah, before we talk about heat transfer yet, okay, let's see. Let's talk a little bit about what the flow look like, okay? What does flow look like inside the pipe? Okay, I'm talking about the fully developed region, okay? There's an entrance region. When you get flow into the pipe, you know, uniform flow into the pipe, it gradually changes, right? There's a little bit entrance region. It's changing from a fully developed, from a uniform velocity profile, gradually change it to a parabolic shape. Then the shape doesn't change. The velocity profile on each cross section doesn't change. That's called fully developed. Okay, so there should be a velocity distribution. Let me see. There may be, or maybe not. Okay, I think yeah. Then there's a velocity distribution equation 5. Hold on, what is that? Okay, equation 5.96. Okay, so the velocity in this particular problem, we're talking about particular problem. Let's just use u. Velocity u Okay, so the velocity we're talking about in the fully developed region, okay, not entrance. Entrance is short and we don't care too much about it. Most of the region, most of the pipe is a fully developed flow. So the velocity, see, it doesn't change with x direction anymore, right? This is the x direction, right? Okay, it's fully developed. It doesn't change with the x direction, okay? You only change with r direction, radius, is from the center. So we have to use cylindrical coordinate. This is circular pipe we're talking about, right? It doesn't change with theta either. Okay, it only changes with r. When r equal to 0, that's the center of the pipe. You have the maximum velocity. Then the velocity gradually decreases. Okay, to the wall. Wall will be non-slip condition with 0. So you have a velocity equations for this. 1/4 times mu dp dx r square minus r square. Okay, so for the laminar.
I'm sorry. What is that symbol? Is that mu you said, or what was that?
Mu is the dynamic viscosity.
Okay, so is that an M then, or is that N?
What is that? Mu.
The symbol for above for the big formula that you just put up there.
U, that's the velocity. You can say V, doesn't matter. I'm talking about a practical problem here, so I give a U. Velocity. I'm talking about the velocity profile. Are you following me? Do you follow me? I'm talking about velocity,
Yes,
right?
sir.
What the flow look like. So it's a velocity I'm talking about, okay? Okay, so previous slides, we talk about the frictional force, right? Sometimes we care about the velocity too, okay? The velocity is not a uniform velocity, do you agree? It's a changing velocity, right? On each cross-section, the velocity has a profile like this, which in the center, you have a high velocity. On the wall, you have 0 velocity, and it's a gradually change on each cross-section in the fully developed region. And these velocity profile on each cross-section doesn't change anymore, okay, along the flow direction. So anytime you get a cross-section, you have the same profile, which on this cross-section velocity is only change along the r direction. This is why it's function of r only. Okay, does that make sense? Is that clear to everybody? Okay, just jump in. We have a small class today, so any question, I want you, all of you fully understand what I say.
Where's our big R? That's the whole length.
That's the radius of the pipe.
Okay, and then little r is that labeled right there, or?
Little r is a variable. It's a function. So that means the velocity change. I can draw it here. Oh. This is a cross section, okay? Velocity in the middle, okay? In the side, it gradually becomes smaller, okay? Its radius. Do you know the cylindrical coordinate? You know, it has to know something, right? Cylindrical coordinate, it's not XY coordinate. The independent variable in the cylindrical coordinate is r, theta, and x. Do you remember that? So the r is changing based on different r's. It's a variable. Okay, if r equal to 0, that means center. Is that right? If r equal to capital R, that means it is on the wall. Okay, it's a function. So the velocity value changes with r. If r become bigger, different values on a different location. So on this surface, on any location, on a surface like this, you have any given location, right? If you want, your goal is to find the velocity with this function, with this equation, find the velocity at any different locations. Okay, I put a lot of dots there. Is that right? On any different location, on any dot, you will have a velocity, which is going into the paper, okay? This is the r direction. So basically, every point, you will have an r. Okay? Every point has a different r, right? Give me some response, guys. Let's talk to each other. It's just 6 of us.
Yes, sir. I got you.
Okay, okay. So give me some response when we talk about this. Okay, so every r you have a velocity calculated based on this equation. Okay.
Dr. Zhang,
Yeah,
is that dp dx or df dx?
dp dx. Yeah, I was about to talk about this. This is the pressure drop. The pressure change along the x direction, dp. Okay. Let me erase here. Okay, interestingly, you can find your velocity on any location inside this pipe, basically, based on this equation. Okay, if you're given a different R. So in the pipe, think about this. You can pipe, you can find the actual distribution. This is for laminar pipe flow. Okay, so look at this. R is actually less than capital R, right? Any point in the pipe. Yeah, is that right? The lowercase r always less than the capital R, right? Is that right? Inside capital R is actually the radius of the pipe. Okay, it's no way you can exceed the radius. Okay, any location you have a any location you have a distance to the center, so which is R, right? So this term is negative. Why the velocity then become negative? What the heck? It's not negative. So what is the reason?
The pressure drop.
That's right. Your mu never be negative. That's a property, but this thing is always less than 0. Pressure always drop, always loses, always loss. Okay. Then pressure increase only happen when you supply energy to it, right? You give power to it. You put a pump there, the pressure will increase. Otherwise, pressure always decrease. Okay, because there's friction. Okay, pressure always decrease. This term is always negative. That's why your velocity is always positive based on this equation. So this is a laminar velocity distribution. Okay, but turbulent then is different. You don't have equation for turbulent. And the turbulent, you don't need the equation. Okay, that's a fully developed. Turbulent flow is really chaotic. You don't have an equation to describe it. Okay, however, well, we like chaotic. If it's chaotic, if it fluctuates, but it fluctuates about a mean value. Okay, and the velocity deflection region, see, look at this parabolic shape for the laminar flow. You have a lot of region in the pipe, you have a decreased velocity. Okay, it's really a gradual change from the maximal to 0, which is bad for us because you have too many different velocities inside the pipe. Okay, but turbulent, although it changes every time to time, chaotic always fluctuates. You never see the same turbulent flow field every 2 different times. Never see they're identical, never. But it fluctuates about the mean velocity. If you use the mean velocity, you will see, hey, there is a very, very tiny region near the wall. You have a very small velocity. Most of the region inside the pipe are all similar. In terms of mean velocity, are all the same. Okay, did you see the difference? So I don't care in the practical application. I don't care actually the fluctuation. I care about the mean velocity. If the mean velocity is similar to the characteristic velocity of the pipe, that's good for us. Okay, so I don't need a velocity profile like this equation. So there's no equation like this. Okay, so basically we always look at the mean velocity. Okay, if you can determine the mean velocity, that's it. It seems like a uniform flow inside the pipe. Do you see my point? Uniform. It's the most chaotic situation become a perfect, easiest situation. If you treat it as the mean velocity, average velocity, it become a uniform velocity inside a turbulent pipe. Okay, if I don't care about 2% of the error in the real engineering application, if I really don't care about that 2%, 1% error, I just treat it as uniform velocity for the pipe. Always talk about the mean velocity. Okay, So a turbulent pipe flow is good for us. So we don't need to worry about the velocity distribution whatsoever. So it's just use the mean velocity, average velocity. That's it. Okay. So good thing is 99% of the flow you see in the industry around here is turbulent pipe flow. Okay, which is good. Okay, so this is the velocity characteristic inside the pipe. Okay, velocity characteristic. Any questions so far? So far, so good. Now we're going to look at the heat transfer characteristic. Heat transfer characteristic is more complicated. Okay, so we're gonna focus on iso heat flux. Well, that's what this book is the focus about, the textbook. Because in the realistic pipe flow, most of the time, if you heat it or cool it, it's always constant heat flux goes inside the pipe. Okay, never you can maintain a constant surface temperature. Okay, it's very, very difficult to maintain, but it's very, very easy to give a constant heat flux. Okay, so it's just heated. Okay, so uniform heat flux is very easy to achieve. So with this condition, for laminar pipe flow, you have a temperature distribution. It's very long. Let's write it down whatsoever. Okay, so the temperature distribution, it depends on your cool or heat, right? If you heat it, bear with my drawing. If your T-wall is higher, you don't know the T-wall. T-wall is not even constant, right? If the T-wall is higher, then temperature distribution become like this, okay? There's something called TC, the center temperature, okay? It's a very important criteria, okay? So center temperature, that's why sometimes we measure the velocity field, measure the temperature field, you measure the center temperature of the pipe. It being used a lot, center temperature, okay? So equation phi 100 is also using the center temperature. It's a reference to the center temperature. Any temperature inside of this pipe equals 1 over alpha. What is alpha? Do you remember? That's thermal diffusivity, okay? It's rho Cp divided by K, right? Partial T, partial X, U. U is the inflow velocity, R squared over 4 times R over R squared minus 1/4 of R over R to the power of 4. Okay, this is a long question, but it is actually an analytical solution. Look at the derivation on page 254 to 255. Okay, that's a derivation for that equation. With the isothermal boundary condition, conclude this equation you can use. Okay, as long as you have the center temperature, you should be able to find the temperature everywhere inside this pipe. One thing is the partial T, partial X. I can put a dt dx if it's 1D. Okay, dt dx has to be constant. Okay, in the convection pipe flow, it is constant. Okay, and you can easily measure to get the dt delta T over delta X by the inlet center temperature and the outlet center temperature, T outlet minus T inlet divided by the length of the pipe. That's the temperature change along the length of the pipe. So it's dt dx, easily measured. Okay, so it's actually a linear distribution of the temperature inside it. So your dt dx should be a constant. Okay, so this is the temperature. So also, it's not easy to characterize temperature by only knowing the center temperature. So we introduced something called a bulk temperature. Okay. Bulk
Quick question, Dr.
Yeah, yeah,
Zhang.
sure.
Over there where we have our TC all the way at the end, that's R over R squared to the fourth, or is it just
R over R square parentheses, then power of 4.
okay,
Similar
gotcha.
fashion, the first term, R over R parentheses, power of 2. Okay. Bear with my writing. I'm writing on my whiteboard pretty difficult. You know, it's equation 2.100 in the textbook. Okay, you can refer to that. Okay, so we need to introduce something called bulk temperature. Bulk temperature. It's the average temperature, basically, on a surface, on a cross section. Okay, it's called energy average the fluid temperature across the tube. Okay, so across the section, basically equation 5.102 tell you how this bulk temperature is defined. Okay, it's the average temperature. So let's write it down here. T bulk, let's say TB is a bulk temperature. Basically, it's the average temperature inlet and outlet, right? So equals to TC plus 7 over 96 U velocity times R square over alpha. Okay, it's an analytical solution based on this. Okay, based on this equation, you take integration, you can find this. Okay, so again, it depended on the center temperature. Okay, center temperature of the fluid. Okay, so this is the bulk temperature. So every cross section you should be able to calculate the bulk temperature. Also, wall temperature. Okay, they're not constant. They change along the pipe, right? Also, on any location, you have a T center. Okay. Similar fashion. Okay. So you have this two temperature, and then your heat transfer, total heat transfer will be Q times A TW minus TB, right? And based on this calculation, actually you can calculate. Let me just give you. I'm skipping equation 5.103, 5.15, 5.16. It's too long for me to write. What's useful to you is a heat transfer coefficient. It's actually equals to 48 times divided by 11 K over D. Okay, DO is just diameter. Be careful. Previous equation are radius. Here it's diameter. Okay, so what is your Nusselt number? It's a good thing for the pipe flow. Pipe is really, it's become easy. HD divided by K, right? Oh, it's K over D, okay. It's actually, there's a certain value. Okay, these are analytical solutions for the heat transfer in the laminar pipe flow. So temperature distribution, we introduce a couple of different temperatures, bulk temperature and the wall temperature. Then we introduce the heat transfer coefficient. Okay, then your Nusselt number will be 4 times 364. Actually, it's a constant value for your Nusselt number, but your heat transfer coefficient will change, depend on the diameter, depend on the K, right? The actual H value is not constant, but your Nusselt number is a constant, okay? But you will ask, is this a local Nusselt number or overall Nusselt number? It is an overall, it doesn't change. You see the local, whatever local value, it doesn't change because the Reynolds number doesn't change in the pipe flow. So mathematical point of view, there's a constant Nusselt number. The heat transfer coefficient is constant, okay, along the pipe. Local heat transfer coefficient is constant. So if you average it, you will become same value here. Okay, it doesn't change with X. It doesn't change with the length. Okay, please change this idea. You know, in the surface plate, in the flat plate, we covered in the previous 3 classes, it's Reynolds number, heat transfer coefficient is always changing. Okay, along the x direction. Here, it doesn't. Okay, it's basically constant. In reality, if you measure it, it's probably varies a little bit from place to place. Okay, but because it's in the measurement, it's not ideal condition. If it's the ideal condition, it's basically just constant. Okay, and then your overall and then your local become the same h and the same Nusselt number. So you only need to remember this. Okay, you have less equation to remember for the pipe flow. Okay, I think I'm out of time. Don't have time to finish to talk about the turbulent equations. Okay, but we did complete the flow phase. Okay, for the flow, you care about the friction, right? Friction force, friction loss. Okay, we have all the equations for the friction. We have the Moody diagram. Okay, to find the friction coefficient. Okay, then for the velocity, laminar, and the turbulent we introduced. The velocity, laminar, you have a distribution, you have an equation for the velocity profile, okay, function. And for the turbulent, it's easy, just uniform velocity all the way through from the beginning, okay, nothing changed. So velocity and the frictional. Flow phase, we covered, okay, completely covered. The heat transfer, we covered the laminar heat transfer, temperature and the heat transfer coefficient. Okay, next time we're gonna talk about the turbulent pipe flow, the temperature and the heat transfer coefficient. Then that's about it, and we will do some example. Okay, is that good? I have 2 minutes. Any questions? That's good. Good to go. Okay. So have a great Friday afternoon. Have a good weekend.
Quick question for you, Dr. Zhang.
Sure, sure.
For that project we've got on Excel, do you want it to be like, you want it for both trials where to show like the data and the information, how to just like link up all like that, or is just one fine?
No, I think the software is what I'm looking for. Okay, it's not really the example 5.5. Okay, example 5.5 is the data for you to test your software.
Yes, sir. Like I have the software like for an overall if you wanted to change it, but I didn't know if like you wanted me to copy and paste and redo it again for like if it was like trial 1, trial 2, like just keep doing the software over.
I don't like the copy and paste part. You know, I want you to pull it down the row and it can do the calculation by itself. Okay, you only need to enter the input value, initial value, or the property values.
Yes, sir. Yes,
okay.
sir. I got you.
Property values. Then you let the computer do the interpolation for the properties and
okay.
then do the calculation. Okay. Yeah.
Yes, sir. I got you.
Okay. Yeah. Okay. So have a good weekend, guys. See you next week. Next week I will be in Lake Charles.